Go for it.
Right, jy kan begin.
Good afternoon, grade 10s, and welcome back to another physical sciences class. Today we are going to finish up what we didn't get to yesterday, okay? And then we're going to carry on with longitudinal waves. Before we start, what I've done is I have gotten together all the links for you guys for this week, okay? So now, if you look in the Q&A, whoopsies.
I'll quickly go check. Just go on. I'll quickly go check what's wrong with the Q&A.
Are we having problems with the Q&A?
Seems like it, yes. I'm quickly going to see what the problem is.
Okay. Right, so we've got a slight problem, it seems, with the Q&A. So we're going to do this old school. I've dragged it back on here. Dum, dum, dum. We're going to zoom in by a lot. And I'm going to shift it up. Okay, let's make that thing go away too, and you can see it properly. Okay, so there is the highlighted one, the link for tomorrow's lesson. Ah, I see it's finally appeared in the Q&A. Cool, cool. So I can pull this one away again. Let's send it back to where it came from. Dum, 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 dum. Ta-da. Okay, that's better. So you now have in the Q&A, you have the link, okay? And that is for tomorrow's class, okay? We're going to do it like this every single day, okay? So that you have the link for the next day. What I'll also do is I will post it again at the end. Okay, another link that needs to come your way is the link for the Google Drive. It is the same link as yesterday, okay? It's not a new link, okay? It is the same link as yesterday. So you've now got the team links for tomorrow and you've got the Google Drive link, the same one as yesterday. Gordley's asking, how does Snaplify work? Miss P, hello. Letabo, hello, hello. Hey, Ash. Okay, so let's quickly answer Gordley's question, and then we're going to go and finish up what we did yesterday. Okay, Gordley, Snaplify is an app that you can download. I've got it on my laptop. Let me be brave. Close all the windows. There it is. There at the bottom. Okay, so you download the app onto your computer, and then you go onto the internet and you go to snaplify.com. All right, you create a profile for yourself, and then you can download on the internet any book that you like. Okay, any book that you want. There's lots and lots of textbooks. And then what you do when you go back to your device, okay, that you have Snaplify on, so either your phone or your laptop, then they automatically sync up, okay, and then you have all those on your computer. I hope that that helps a little bit, Gordley. Can't open links from the chat. You've got to copy and paste it. Okay, so you guys need to screenshot it. Make sure you have it for tomorrow. All right, so let's get going in terms of what we did yesterday. This is what we started with yesterday. So I'm going to zoom through it because we did all of this yesterday. The stuff we didn't get to was period, frequency, etc., etc. Okay, so Cool, Dilo. If you get the emails from Teen Africa, that is awesome. Okay, so let's get back to some actual thinking. Let's focus. The period of a wave is the time taken for one complete wave. It is time, so it is measured in seconds. The frequency is the number of waves per second. Okay, now we've got a way to go from period to frequency. So if I have the frequency, I can calculate the period. So 1/f gives me period. And if I have the period, 1/t gives me the frequency. Okay. Whoops. Go back. There we go. Right. So there is period and frequency. Period is measured in seconds and frequency is measured in hertz. Okay, so it's pretty easy, pretty simple to go from the one to the other one. Now we get to wave speed. Okay, speed means how far do I travel versus how long it takes me. So the definition of wave speed is the distance traveled by a point on a wave per unit time. Okay? Hello guys. Ooh, you guys were a bit late, nah? I'm gonna make you do push-ups for that. Okay. Sorry guys, I've been teaching so much. My voice is taking a little bit of strain. So, wave speed, we can write as V equals F times lambda. Okay, that funny sign there is called a lambda. So F is a wave speed. Speeds are in meters per second. Frequency is in hertz. It is the number of waves per second. And lambda is the wavelength. Okay, and we give that in meters. Someone asked if they couldn't log in yesterday. Did they miss a lot? All the stuff that we did yesterday is in the drive, which I put the link into the Q&A. Don't panic if you missed it. I will put the links in again at the end. Okay. Right, guys, so we've got an equation for wave speed. But now, we can write frequency as 1/t. So, we could also say that the wave speed is lambda divided by period. Okay, you can use either of these. It just depends on what you get given. Okay. Now, fortunately, guys, these formulas are on your information page. So you do not have to memorize them. Okay, you must just be able to use them. Right. So, I'm going to run you through a question and how I would approach it. Then, there is another practice question that you can try. Okay, so I'm going to put it on. I want you guys to either screenshot it or remember this is in the slides. Okay, and then I'm not going to give you the answer for the second one. I'm only going to do it with you tomorrow. Okay, that's how homework works. Right, so we have ripples in a wave tank. They are produced and have a wavelength of 18 millimeters. And a speed of 0,2 meters per second. So the questions are, firstly, calculate the frequency of the wave, and secondly, calculate the period of a wave. Now I'm warning you beforehand. that there's two ways of calculating period. Ollie needs me to go back. Those of you who weren't here yesterday, I haven't now suddenly got like a mirror next to me that I keep on checking, okay? When I'm presenting on my laptop, the screen I see, okay, is the screen you see next to your face. That is exactly what you are seeing, okay? So what ends up happening is I can't see the Q&A. So what I've done is I've got a second monitor next to me, okay? And I've logged in, I've used the same login as you guys have, which means I can see the Q&A, okay? So that's why I keep on dashing off to the side. Okay, I'm trying to make sure that I don't go too fast and I miss your questions. Okay, Ali, I hope you've got this, dude. Let's go back to the question, okay? So we need to calculate frequency and we need to calculate period. Let's start with the frequency. Okay, so there's the problem. Sorry guys, my throat is quite scratchy. I promise I'm not sick. Okay, let's do frequency. Frequency is F, okay? I have wavelength and I have wave speed. So I start by writing down my variables, okay? And very important, remember, wavelength must be in meters. So I've got to convert millimeters into meters. So I have to, yes, Jared, dual monitor setup. It's really cool. So I have to divide millimeters by 1,000 to take it to meters. Okay. Next one that I get given is speed. Okay. And it is in the correct unit. So I don't have to do any mathematical manipulation of speed. Okay. I am asked to calculate the frequency. Okay. Miss P, I did the conversion straight up here. Okay. I took 18 and I divided it by 1,000 so that I can go from millimeters to meters. Okay. So now I've got to figure out which formula I can use. So I'm going to use this formula. So I've got wave speed equals frequency, which is what I'm looking for, times lambda, the wavelength. Right. Now I take my variables and I substitute. So that is my substitution. Okay. Now I want F on its own. So I go 0,2 divide by 0,018. And I get 11,111111111 forever. So 11,11 hertz. Okay. So that wasn't that hard. You just need to be able to read your question carefully and pick out from the question the variables that you need. The person who said 0,9, you went the wrong way. You divided 0,018 by 0,2. Miss P, don't have to apologize. The fact that you saw it is very, very good. Don't apologize. Okay. Remember, guys, you can't learn if you don't make mistakes. Okay. So that is how I would have approached this question. Now, the next one where we have to calculate period, there are more than one way to do it. So I have done both. Okay. Now it completely depends on you which one you prefer. Okay. So Whoopsies. Okay, ignore that for a second. So we have to calculate the period. These are all the variables we now have, okay? We have lambda and we have wave speed, and we've just calculated frequency, okay? The one I would prefer to use is this one, where I take the frequency I calculated and calculate the period, okay? Why? Because there's less math manipulation involved from substituting to getting an answer. It's okay, you're here. Right. The other option you could do is to take the wave speed and the wave length and use the wave speed equation to calculate the period. And you will see that you get exactly the same answer. Are we always going to convert to 2 decimal places? Yes. So I would not choose to do the second option that I put down here for you, simply because there is more maths involved at this point. Okay. However, if I think about it, using the second option, I'm using the facts they gave me and not something I calculated. So it really is up to you, whichever one of these two you choose to use. Okay, there's no right and wrong. Okay. Right, so I'm going to quickly pop on another question for you that I'd like you to try. So I want you to quickly just write it down, okay? And I will, I promise, go over that question tomorrow first thing when I see you, okay? So you've got a slinky, and there's a transverse wave in the slinky. It has a frequency of 0.8 hertz and a speed of 24 meters per second. I want you to calculate the period, and I want you to calculate the wavelength. Okay. I'm just going to give you guys a moment to jot that down. Okay. Again, this question is in the slides, and the slides are on the drive if you want to download it. Okay. I have also in the drive put in the week 4 folder a Word document with all the links for this week on too. Okay, so you can go and fetch it there too. It has a terrible delay, I know, sweetheart. Godly, I'm going to pop back quick. Guys, apologies. Okay, so Godly, this one here, I just went 1 divided by 11,11, and that gives you 0,09. With this one, I'm going to talk you through the maths. Okay, so I want to get T. Click on slideshow. I want to get T on its own. Okay, so I don't like the fact that it is a fraction here. So I take T and I multiply it to this side. So now on this side, I've got 0,2 times T is equal to 0,018. Okay, so I've got 0,2T on the left and 0,018 on the right. And now I want T on its own, so I divide 0,018 by 0,2. Okay, I hope that helps. Ma'am, do you have the maths link? We're going to ask the moderator really nicely if he can see if he can find the maths link. Okay, I will try and organize to get you guys the maths links as well. Okay. Sorry, guys, I didn't think that far. Moderator says he'll have a look. Thank you, moderator. He's awesome. Okay. All right, Corley Marie. I hope that really helps you. Okay. This is why I wouldn't have done this way around. I would have done this way. Okay. Right. So there is the problem that I want you guys to have a look at. Okay. Have a go at it. Try it. See what you get. Okay. Cool. So guys, today we are looking at longitudinal waves. Okay. Now, a lot of the work in longitudinal waves is exactly the same as in transverse waves. Okay. So don't panic. Okay. Right. Oxford successful, 88 to, that's wrong, it should be 97. Sorry, guys. Sorry. And then study and master, I think it's round about page 110 or so. Okay. So, a longitudinal wave. Oh my goodness, we start with the definition. Think about transverse waves. Transverse waves, we said, direction of displacement of the medium is perpendicular to the direction of propagation. Transverse. Longitudinal, the direction of displacement is parallel to the direction of propagation. Okay? It gets squashed and let go. You guys didn't get the question. Oh my goodness. Okay. At the end, I will pop it back on for you. I promise. Okay. Lots of you not getting it. I will pop it back on. Thank you, Mr. Moderator. Guys, there you all have the maths link. Okay. Awesome. I promise I will give you the question at the end. Okay. So, the picture of a longitudinal wave will come now. I was cheating a little bit with this one because you guys know my drawing skills, like they have limits. So I went and got one off the internet. Okay. Now the old words that are the same for transverse and longitudinal waves. Wavelength, definition is the same. Distance between two successive points. Okay. The amplitude is the same. It is the maximum displacement of a particle in the medium from its equilibrium position. Okay? Got it? Same. This is exactly the same words as we use for transverse. Okay? The other words that are the same are the ones we did today, which is frequency and period. Okay, guys? So this is for longitudinal and for transverse waves, these concepts are exactly the same. But now, because a longitudinal wave is a squash and a let go, and a transverse wave is an up and a down, we needed new words to describe some of that wave. Okay? Cool. So, let's look at the new words, right? So we've got refraction, which is a space of low pressure. Now I can see a lot of you looking at me going, okay? Low pressure means the particles are far apart. Okay. The definition of refraction you have to know as a region of space of low pressure in a longitudinal wave. But for yourself, explain it as the particles are far apart. I'll show you a diagram. Okay. Next one up is the compression. So it's the opposite of a refraction. A little bit like the crest was the opposite of a trough. Okay. So refraction and compression are the words we replaced crest and trough width when we talk about longitudinal waves. So if a refraction is a space of low pressure, compression is a region of high pressure. Now, I find this definition easier to remember, okay? So I use the definition of compression to get to the definition of refraction, if that makes sense. Lessons is 35 minutes. Okay, so sorry for the puppy in the background. So when I compress something, think about a balloon, okay? I take that balloon and I squash it, okay? There's a lot of pressure in this balloon, high pressure. Why? Because the particles are close together, okay? So that is how I use the definition of compression to get to the definition of rarefaction. Okay, moderator, we've got like 2 or 3 different types of textbooks in here. I have 2 of the many textbooks, so I try and give them the pages. So D. Lowe has got a study and master, okay? So he helps us out a little bit with where it is in the study and master. And then for the kids with the Oxford, that's the one I use. Okay, cool, guys. Let's look at what a longitudinal wave looks like. Ta-da! Right, so wavelength is the length between 2 successive compressions, or it is the length between 2 successive rarefactions. Okay, so can you see that with a compression, I squish the particles close together, and with the rarefaction, they are far apart. Can you guys see why I didn't try and attempt to draw this thing? Okay, right. You see why I didn't try and draw this thing. Now, you are generally not expected to draw a longitudinal wave like this. And the worst is that most people draw a longitudinal wave to look like a transverse wave. Okay, very mean for your brain. Okay, yes, Jared, but I don't know if it's cute puppy noises or yappy puppy noises, but that's fine. Okay, so this is what a longitudinal wave looks like. Right, guys, wavelength is the same concept. Frequency, period, wave speed, all of these are the same concepts. So I would do all calculations in terms of longitudinal waves exactly the same as I would do them for transverse waves. Okay. So why is it important for us to know about longitudinal waves? DJ, so sound is longitudinal waves, okay, and light is a transverse wave. What is the space between 2? What is the space between 2 bumps? That is also a wavelength. Okay, all right, so when we do longitudinal waves, we have to look at sound, okay? Now, important about sound is that they are exactly longitudinal waves, okay, parallel, but that they cause regular variation in the pressure, okay? So a sound wave is a regular longitudinal wave, okay? I know that sounds weird, sorry, but that's the best way I have to describe it. Okay, so sound waves are longitudinal waves which cause regular variation in the pressure of a medium. Okay. Now, this is something that I know you guys struggle with. So let's go a little bit slower. Okay. When you guys are all out of lockdown, I want you to try this experiment. Okay. You're all going to stand very close together, very, very close together. And you're going to have someone push one of you, okay, from the outside. And then I want you to see how long it takes for everybody to fall over. Okay? This is an example of solids. Particles are close together, so if I bump a particle here, it quickly travels and bumps the next particle. Okay? But if the particles are very, very far apart, it takes a very long time if I bump the one particle for that particle to bump the next. Okay, so speed of sound is slowest in gases and fastest in solids. Okay, the speed of sound in air is normally taken as 340 or 343 meters per second. This is not a value you have to go and remember. Okay, this idea, however, you need to. So because particles are far apart, the speed of sound is slow. When particles are close together, the speed of sound is fast. Okay, that's quite an important concept for you guys to keep mind of. Okay, now when we talk about sound, there is three concepts we have to think about. Okay, pitch. So how high or how low a sound is, which depends on the frequency, okay? If a sound has a high frequency, it has a high pitch. You hear a high sound. If it has a low frequency, then you hear a low pitch, okay? Now, very important, our ears can only hear between 20 and 20,000 hertz. The other wave is an up-down wave, so it goes tung, 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 up, down. It doesn't get squashed together like this. Okay, so we can only hear between 20 and 20,000 hertz. All right, sounds below it is called infrasound. I know, weird. And sounds above it is called ultrasound. Word ultrasound. I know that word somewhere. Okay. So then from pitch, we go to loudness. Okay. Loudness is how much energy something has. So the bigger the amplitude, the louder the sound. But now you need to be careful. All of us have ears that are differently sensitive to different frequencies. Okay. Sometimes there will be one sound that like you hear it and just you can't deal with it, okay? And that is because your ear is sensitive to that particular frequency. It's not the same for everyone, okay? But if there's a sound that is being played and your ear is very sensitive to that frequency, that note will sound louder than other notes because your ear is more sensitive to it. Okay, so we've done pitch, which is equal to frequency, and we've done loudness, which is equal to amplitude. Okay, the last one is quality of sound. Okay, now I put it all on here, and I know it's a bit like in your face, but just think. I can speak at the same pitch as someone else, but it sounds different. A guitar and a piano and a recorder and a bagpipe, they can all play the same note, but your ear hears it differently. And that's because they have different tones. And these tones are caused by different wave forms. Okay, now you're all going, what? So I thought I'd show this to you, and this is not required in depth, guys, so don't panic about it. A pure note has a smooth, perfect sine or cos waveform, okay? But the human voice has got ups and downs, sometimes like little vibratos, all sorts of weird things. So the human voice doesn't have a pure note, okay? That is why we have depth to our voice. That is why you can hear it's a saxophone. is because each of these instruments, each person's voice has this very unique waveform. You are not required to draw this, okay? You are not required to put it into a lot of detail, okay? The detail you need to know is that two notes of the same pitch and loudness sound different because they have different tones, and this happens because their wave forms are different. Okay, that is the important bit in terms of quality of sound. Okay, right, last little one. Dum, dum, dum. Ultrasound. Okay, ultrasound, guys, is a form of sound wave. Promise. Okay, it's a squashing and a let going of a wave. We use it in medicine. Okay, that is what an ultrasound scan would look like. So it is a frequency higher than you can hear, somewhere between 20,000 and 100,000 hertz. You don't need to know that number. You need to know it's a frequency higher than the range of human hearing. Okay? Again, if you think about it, if we use the equation, the higher the frequency, the shorter the wavelength. Okay? They are inversely proportional. Miss P, what did your teacher tell you but you didn't understand? Okay. Short wavelengths have got short little up and downs, so they can see small objects easily. Okay. We can't hear the sound. It's beyond our range of hearing, but we have invented machines that can. All right. Now, the details of ultrasound, you don't need to know. Okay, you don't. But I thought it would be nice to just quickly chat through them. All right. Let me just check what's going on the chat. Cool. Okay. So again, you don't need to know the mechanisms of ultrasound and how it's detected. Okay. But I personally think it's nice to just kind of have half an idea of how the stuff works. So here it is. An ultrasound scan, you can see how quickly I type, creates an image of internal organs. So the ultrasound wave moves, and then it hits some other boundary. So for example, you've got a muscle that's attached to the bone. Okay, that is a boundary. Then what happens is when it hits the boundary, part of the wave is reflected, part of the wave is absorbed, and the other part carries on going. And every time a wave is reflected, the computer picks up that reflected wave and makes an image. Okay, so that is in brief. Here, there's no frequency of the sound barrier. It's the speed of the sound barrier. Okay, so here, if something moves faster than 340, you hear a boom. Okay, it's closer to 350. You hear a boom, okay, and that means that they are moving faster than the speed of sound. Okay, that's what it means. Okay. So this is roughly how ultrasound works. Like I say, guys, you don't need to know the details of this. Okay, but I do think it's nice to have an idea of how medicine has used this technology for us. Okay. The advantages, and these you can figure out for yourself, guys. Okay. It means that I don't have to operate and find. Oh, Miss P, I get it. I'll get there now. It means that you don't have to operate and find things that are wrong. Okay, X-rays emit a lot of energy. We're going to do that tomorrow. In physiotherapy, they use ultrasound to reduce swelling, and they can even use ultrasound to break up kidney stones. Okay. And that's my story for today. Okay, I will go back to the question that you guys asked for. Miss P, when we hear sound, okay, the vibrations hit our ear, okay, the frequency, and the frequency makes bones in our ear move, and those bones turn that movement into impulses, okay, electrical impulses that our brain can do something with. Now, our ear is only sensitive enough to pick up certain amount of vibrations. So if the vibration is too fast, then our body is not able to do anything with it, okay? So when the frequencies are too high, then our ears, they're not fine enough. So all it does is the bones just go brrr, and then they almost don't move, okay? Where if the sound's frequency is too low, the vibration of the bones are so slow that our body can't pick it up either, okay? And that is why there are limits to what frequencies we can hear, okay? It's not been proven, but there is lots of research that shows that certain animals can detect frequencies lower than human hearing as well as higher, okay? This is often why you'll find that before an earthquake or like tsunamis and things like that, the animals get very restless because that movement of the earth deep, deep, deep below cause an ultrasound or an infrasound frequency, okay? It's very strange. It's like a huge thing. Can what kill cancer? Ultrasound? No, ultrasound can't kill cancer. Okay, so I'm seeing lots of questions. Let's deal with it. So again, I've given you the Microsoft Teams link for tomorrow, and I've given you the Google Drive link. It's the same Google Drive link as yesterday, and it will still be the same Google Drive link tomorrow. Okay. There is a document in with all the meeting codes for this week for you in folder week 4. Okay. Then the video, okay, you guys need to remember that all the videos go onto YouTube. It goes onto Africa Teen Geeks, okay? And we've created playlists so you can go and find the grade 10 physical sciences playlist or the grade 10 maths playlist, okay? You can go and find the playlist for you, okay? And the dates for each are on there. So you can correlate the video you're watching with the notes that you can pull off the drive, okay? Then, guys, if you haven't already done so, okay? Tyler, I'll explain now. Okay, whoa. Ma'am, what are these links for? So, the first link, the one that says teams.microsoft.com, that is the link for tomorrow's lesson. Remember, I said to you guys that the links are going to change every single day. So to make it easier for you to find, I'm going to post the link for tomorrow in today. And tomorrow I'll give you the link for Thursday. Okay, so I'll give you the link every single day like that. Then the second one that says drive.google, that is the link for a drive that I've created for you guys where all the notes and everything are in. Okay, so your brain can't process it because it's high hertz. Yes. Okay. Sound, how long does it take sound to reach your ear as far as you're standing from it? Okay. All right, guys. I think that is it. So you have a little bit of homework. I really want you to try it. Okay, it's not hard. And then tomorrow we're going to look at electromagnetic waves. Okay. And then Thursday we're going to look at energy and waves, which is quite important because you take it to matric with you. Okay. And then on Friday, I will show you guys the favorite question that all teachers like to ask, and I'll show you how to approach it. Okay, that will bring us to the end of this week. Next week is a very short week. Monday is a public holiday, 27th of April. Friday is a public holiday, the 1st of May. So we only have Tuesday, Wednesday, and Thursday together. Okay, so what I'm going to do next week is I'm going to start with the electricity module. Okay, now you guys get a bit of a choice here. Okay, there are 3 components: electrostatics, magnetism, and electrical circuits. We can either do electrostatics and magnetism in those 3 days, or we could do electrical circuits. And this is up to you. Okay, so you need to have a think, and I'll keep on asking and we can figure it out. Okay, right? And then we take it from there. All right, guys, thanks so much for watching. I hope you have a fantastic day, and I will see you guys again tomorrow. Bye.